So chapter 6 is involving more identities. Specifically in chapter... Can we stop talking, please? Thank you. In chapter 6, we're going to be developing a new set of identities. So chapter 6 is going to feel fairly similar to chapter 5 in that regard. We're going to start with angle sum and difference formulas. So I want to be able to figure out an identity for, like cosine of the sum of two angles, or the difference of two angles, or the sine, or the tangent, or whatever. I want to develop some formulas for that. So the very first one we're going to derive geometrically. What I'm about to do is not something I'd expect you to reproduce. So this is something you could just kind of, pay attention to and try to follow. You should understand what we're doing, but I would not expect you to be able to reproduce this kind of thing that we're about to do. So this is like a derivation. We're going to develop a formula for an angle sum or difference, and we're going to use geometry, some geometry techniques to kind of get that. Okay? All right. So let's start by just considering two angles in standard position. So maybe I have this angle here that I'm going to call V, and then say an angle down here. We'll call that one U. And then let's talk about this angle here. I'm going to call that angle theta. So what is the relationship here between angles U, V, and theta? Is there an equation I can write that relates these three angles together? Well, if you notice, I can say theta is the same as U minus V, right? Theta is the gap between the terminal sides of U and V, right? So if I subtract the smaller angle from the bigger angle, should give me the gap between the two terminal sides, right? Everybody buy that? Okay. So if I want to talk about angle theta, I can write that as a standard position angle. Here, right? And it's okay to do that. Why is it okay for me to move my angle theta there into the first quadrant like that? Because all I'm doing is a transformation, right? I'm just picking the thing up, moving it, and rotating it. None of that changes the size of that angle, right? The size of that angle is maintained throughout any of those transformations. Okay, so what I'm going to do now is I'm going to define some points on these angles. So if I pick the point here on angle V as the point that intersects angle V on the unit circle, if that's a unit circle point, what would the x and y coordinate of angle of this point B be? Well, it would be cosine of V comma, sine of v, right? The point's on the unit circle, the x-coordinate is cosine of that angle, and the y-coordinate is sine of that angle. That's part of how we defined, or how we developed that unit circle, right? Similarly down here, I'm going to call this point A. This is going to be the point on the unit circle that intersects the terminal side of angle U. So the point here would be cosine U, comma, sine U. Everybody okay with that? All right. I'm going to do something similar over here on theta. So I'm going to call this point on theta A prime. And this would obviously be cosine theta, comma, sine theta. And I'm going to define this point down here on the initial side of angle theta. And this is, I'm going to call this point B prime. And this is just 1, 0, right? Okay. So now what I'm going to do is I'm going to imagine the segment that's connecting A and B, and then A prime and B prime. What can I say about the relationship between the length of these two segments? If angle theta is the same size, right, and points A, B, and A prime, B prime are all on the unit circle, that means that, like, those things are congruent, right? Everybody kind of remember that? And we know that this angle is congruent. So this looks like a side angle side congruent triangle to me. So I know then that congruent parts or corresponding parts of congruent triangles are congruent. So I know the length of segment AB has to be equal to the length of segment A prime B prime. Right? If those triangles are the same size, then the sides have to all be the same, right? Everybody okay with what we did there? All right. Now I want to do is I want to calculate the length of these two segments. In geometry, how would I calculate the length of a segment like this that's defined in the XY plane? What was that? Distance formula is exactly what I'm going to use. Do you remember the formula for the distance formula? It's basically the Pythagorean theorem, right? It's the square root of the difference of the x's squared plus the difference of the y squared. So for AB, we're going to have x2 minus x1 squared plus y2 minus y1 squared. And then for A prime B prime, we have 1 minus cosine theta squared plus 0 minus sine theta squared. Everybody okay there? And now I'm just going to work on kind of manipulating this equation. So if I want to simplify this down, what would be the first thing that I can do? or the first thing I should do if I want to simplify this down. Let's get rid of the square roots. How can I get rid of the square roots? I just square both sides, right? And then those go away. Okay. What else would I want to do then? I probably want to get rid of the squares, right? I can't square root both sides because then I'd be back exactly what I have here. But what I can do is I can multiply those out, right? Because cosine v minus cosine u squared, it's just cosine v minus cosine u times cosine v minus cosine u. So you just FOIL that out, right? So I'm going to write that FOILed out part here below. I'm not going to show the foiling though because it's, I don't know, tedious. Too tedious for me. I can FOIL in my head, so I'm going to take advantage of that. And I'm going ahead and FOILing everything out right now. So that's the left-hand side. And then the right-hand side is that. Everybody okay with what I did there? Just FOILed everything out, basically, right? Now let's look for things that we can do with that now that it's all FOILed out. I see a whole bunch of nice things happening. I see cosine v, or cosine squared v, plus sine squared v. What's that going to give me? 1. I see cosine squared u and sine squared u. What's that going to give me? 1. So on the left-hand side, I'm just going to put a 2 there from the 1 plus 1. And then I still have the minus 2 cosine v times cosine u. And the minus 2 sine v times sine u. And if I look at the right-hand side, I see a cosine squared theta and a sine squared theta. What's that going to give me? 1 still, right? And if I combine it with this other one here, I have a 2. So that's a little better, right? Things cleaned up there a little bit. But we can still do a little bit better than this. What do you guys want to do next? How about we subtract 2 from each side? What's that going to do? Gets rid of those, right? What else might we want to do? Adam, what was that? Yeah, let's, well, I'm going to divide by -2. I'm not gonna do -2 cosine because you need to have a variable with that because we have 3 different kinds of cosines, right? So we have cosine u, cosine v, and cosine theta. But let's divide by -2. That is a good idea. And what was theta again? U minus v, right? So what we end up with then is cosine of u minus v is equal to cosine u times cosine v plus sine u times sine v. And that's going to be our first identity for the difference of two angles, or the cosine of the difference of two angles. This is the only geometric derivation we're going to do. To get all the rest of our identities today, we're just going to take an existing identity and kind of modify it appropriately using the other identities from last chapter. So we don't have to do any messy geometric derivation from here on out after we've got this one. We can build all of our other angle sum and difference identities off of this. So let's say the next one we want to find is cosine of u plus v. How can I think about this as a difference of two angles? How can I rewrite an addition problem as a subtraction problem? How about minus the negative? Right? That's the same thing as addition. And now I can just apply the formula, the identity that we have above. So cosine u times cosine negative v plus sine u times sine negative v. And if I look at my identity sheet from last chapter, and I look at the odd-even identities, cosine of negative v is just cosine v. And sine of negative v is negative sine v. So I'm going to write the negative here because it's just things being multiplied together. And this is our angle sum identity for cosine. Look at how much easier that one was to get than the previous one, right? We didn't have to do any geometry and any fancy messing around there. We just used identities to get that one. Let's now look at, let's say we want sine of u plus v. Well, I'm going to think of u plus v as just a theta here for a moment, just to make what I'm about to do a little bit easier to see. Okay, so I'm just using theta in place of u plus v. And now I need to figure out a way to rewrite this as a cosine problem. So I'm going to look at my identities from last chapter, and I'm going to use the cofunction identity that says that sine theta is equal to pi over 2, or cosine of pi over 2 minus theta. And now I'm going to put the u plus v back in and distribute the negatives. Everybody okay here? After this hour. And I'm going to group these two together, and I'm going to apply the angle difference formula for cosine that we developed just a moment ago. So I'm going to have cosine of angle u times cosine of angle v plus, sine of angle u times sine of angle v. And if I use my cofunction identity now on cosine of pi over 2 minus u, that just turns into sine u. And if I use my cofunction identity on sine pi over 2 minus u, that just turns into cosine u. And we're done. How do you suppose I'm going to do sine of u minus v? I'm just going to think of it as sine of u plus a negative v and use the identity from above. And my odd-even identities say that cosine of a negative is just positive cosine. And my odd-even identities say sine of a negative is negative sine. And so there's my angle difference formulas for sine. Now, typically, we don't write these as two separate formulas for these angle sum and difference problems for sine and cosine. Usually, we compress them together. So, like on an identity sheet or whatever, the way I would write this is with a plus minus. So the way you read this identity on your sheet of paper would be, if I want u plus v, I'm going to use a minus sign there because I'm going to use the top symbols. Or if I was looking at cosine of u minus v, I'd use the plus symbol there. You guys kind of see how I'm using that? So typically we don't write these as two separate. We write them as just one. So if we do the same thing for sine, those match. Probably make that. So this would be like the way it would appear on an identity sheet or whatever with the plus minuses. Everybody's okay so far? Okay. Now, what if I wanted to do tangent? And we're going to do both tangent formulas at one time because it's not hard to do that. Remember back to last chapter, what is the identity for the quotient identity for tangent? Sine over cosine, right? Okay. And if I use the identities that we've written above, I have this, but this isn't really what I hope to get out of this. It seems kind of weird to have an identity for tangent that's in terms of like sine and cosine. The more standard way to write this would be to write this identity where everything is in terms of tangents. So the trick here to get it in terms of tangents is I'm going to multiply the top and bottom by 1 over cosine u times cosine v. So when I distribute that to the first term, the cosine v's cancel, and I'm left with sine u over cosine u, which is just tangent u. When I distribute to the next term, the cosine u's cancel, and I'm left with sine v over cosine v, which is the same thing as tan v. In the denominator, when I distribute, oops, I meant that to be red, to the first term, both the cosine u's cancel and the cosine v's cancel, leaving me with just 1. And then when I distribute to that last term, I end up with sine u over cosine u times sine v over cosine v, which is just tan u times tan v. And that's the form that we're going to use where it's written in terms of tangents. Everybody okay so far with these 6 identities now? I say 6 because they're plus or minuses, right? So using these 6 identities, we can do some problems. So let's look at some examples of what we can do. Let's say we want to find the exact value of cosine of 15 degrees. Now, if I'm asking for an exact value of a trig function, what are we likely going to have to use? Probably the unit circle, right? Is 15 degrees a unit circle value? Is that a unit circle angle? 15 degrees. It is not. So what I want to do then is I want to find a way to rewrite this as the sum or difference of 2 unit circle angles. So if you look at your unit circle angles, what 2 angles could we add or subtract to get 15 degrees? There's lots of possible answers here. How about 45 minus 30? Those are both unit circle values, or unit circle angles, and they certainly subtract to give me 15 degrees, right? I can now use my angle difference formula for cosine. That's going to turn into cosine of 45 times cosine of 30 plus sine 45 times sine 30. Now these are all in terms of unit circle angles, so I can just evaluate each one of these with my unit circle. So if I go to my unit circle, the cosine of 45 degrees is square root 2 over 2. The cosine of 30 degrees is square root 3 over 2. Sine of 45 is square root 2 over 2. And sine of 30 degrees is 1/2. So when I multiply these together, I get square root 6 over 4 plus square root 2 over 4. And if I add those together, I can't add the radicals because they're not the same radical, but they do have a same common denominator, so I could write it as a single fraction. What if I wanted to do sine of pi over 12? Or 5 pi over 12, excuse me. So here it's a little bit trickier, right? Because the angle this time is written in terms of radians, so you have this fraction to deal with. If I look at the unit circle, though, all of my unit circle angles are in terms of like a third, a fourth, or a sixth of pi. Everybody's okay with that? If you look at your unit circle, you should be able to see that. So all I'm going to do is think about it in this way, where I want 2 digits to put in front of those pi's that'll subtract to give me the 5, and we'll reduce down so that those fractions are in terms of third, fourths, or sixths of pi. So what 2 coefficients could I pick there that will subtract to give me 5 and will cause those fractions to reduce down to give me thirds, fourths, or fifths? So maybe you say 6 and 1, right? That subtracts to give you 5. But if I reduce them down, I get a half and a 12th. That's not going to work. So maybe we try 7 and 2. That doesn't reduce down, right? Okay. Maybe we try 8 and 3. Yeah, that works. Hi, Caden. So that reduces down to 2/3, and that reduces down to 1/4. So I can say then I have sine u times cosine v minus cosine u times sine v. These are all now unit circle values. If I go track them down, sine of 2/3 pi is square root 3 over 2. Cosine of pi over 4 is square root 2 over 2. Cosine of 2/3 pi is negative 1/2. And sine of pi over 4 is square root 2 over 2. And if I simplify this down, I get the same thing that I had before. Square root 6 plus square root 2 all over 4. Everybody okay with that? So the hardest part there is just to figure out like what fractions you need to be subtracting. But given what I've told you, you just kind of start with the 2 subtraction problems that get you what you want, and then you just check to see that those cause the fractions to reduce down accordingly. It's that simple. Don't try to make it harder than that. If you try to start with the unit circle values and add and subtract them to get the 5 pi over 12, that's, I think, much harder than just start with, it's going to be some 12s minus some 12s, and let's just go one by one and check numbers that give you the right or give you the right value. All right. So let's say we want to write this as a single trig function. So notice that none of these are unit circle values or unit circle angles, but that doesn't really matter to us. When I look at this, all I really see is I see sine u cosine v minus cosine u sine v. I recognize that formula if I go to my identity sheet. That's the difference, or the angle difference formula for sine. So that's sine u minus v. So just sine 24. And now I'm done. So that should be pretty easy, right? All you're doing is, can you use the identities to go the other way to compact them down into a single? All right, let's say I want to prove this identity. Cosine of 3x plus cosine 2x is equal to cosine 2x times cosine x. Which side do you think we should be working on? I would work on the left side. Why would I work on the left side? Well, first of all, there's two terms. That's going to be more complicated than one term. And I have a bigger coefficient on the left-hand side. So those are both good reasons to pick the left side. Okay with that? So given that we've just talked about or if I look at the right-hand side, I see that my variables are 2x's and 1x's, right? So I want to find a way to rewrite 3x in particular, so it involves 2x and 1x. Well, hopefully it would seem pretty obvious that I would just do and write that as cosine of 2x plus x, right? And it seems like, well, we have plus cosine there. Maybe that's going to be okay to not do anything to. Maybe I'll just leave that alone for right now. And maybe I might have to do something to it, or maybe I won't. Not totally sure right now. So when I apply the angle sum formula for cosine, I get cosine 2x times cosine x minus sine 2x times sine x, and then I still have that plus cosine x floating around there at the end. So let's look at what we have now. I have one of the things that I'm looking for. I need to somehow get a second one of those, and I have to get rid of the other stuff that's there. So here's the trick. You ready to see the trick? I'm going to rewrite cosine of x. I'm going to rewrite that as a difference of two angles. What two angles do you think I'm going to be subtracting? How about 2x and x? Everybody okay there? The reason I'm doing this is because I know that's going to give me another sine 2x and sine x, and it'll give me another cosine 2x times cosine x. So I think everything will combine together and cancel out appropriately. Let's see when I do that. So this stuff, first two things stay the same. And then I use the angle difference formula for cosine. That's going to be cosine 2x times cosine x minus sine, minus, I'm sorry. It's, they switch. Plus sine 2x sine x. That all on one page. And here, those guys combine to give me 0 now, because I have a -1 and a +1. And the other two are like terms. I have one of each of them, so if I add them together, I have 2 total. And that's exactly what I needed. This is where we're going to stop for today.